Okay, so far we've been talking about things that happen statically. Everything we've talked about are like low frequency, not changing with time. Really, we didn't do anything actively to take the changes with time and the dynamics of the system into account. Now, we are going to start now talking about building the system, the way of thinking and the tools that we'll use to analyze systems that vary with time. Now, this will happen over several lectures, and these tools will be extensively used. So we want to make sure that we understand all of them. Again, it starts simple and rather trivial, but then it builds up. So it's important to understand these tools well. You may or may not be familiar with them at some level, but that's what we are going to be doing. Okay, so the first thing we want to do, I'm going to start very basic. So the first thing we are going to start with is something that I'm sure you're familiar with. Otherwise, you wouldn't be here, which is the fundamental theorem of calculus. Right? What does fundamental theorem of calculus say? It says that if you have a function f of x, right, that, let's say this is the function f of x. So this is x, so this is some function f of x. And if you're interested in determining the area of this function, the area under this curve, say from A to B, it says something quite interesting and remarkable and very useful. It says that the area from underneath this curve, which is shown symbolically by this symbol, the integral from A to B of f of x dx, is equal to a capital F of B minus capital F of A, where capital F, or the derivative of capital F with respect to x, is f of x, where f of x is the derivative of capital F. Or another way to write this, which is commonly done, is that f of x is the indefinite integral of lowercase f of x dx. So this is indefinite. Yes, sure. Yes. Plus c. Thank you. Okay, I guess, yeah, that's true. That's true. But indefinite integral is basically an inverse function, right, of the inverse of the derivative. So, but where does this come from? Where does it come from? The simplest way, there are different ways to prove this, and you can make mathematically complicated or something, but the bare essence of this is the following. So you can say, okay, I really want to estimate this area, right? And what I need to do is just you can break it into smaller pieces. By the way, this is quite remarkable in certain ways if you think about it. And we'll talk about it in a second. But let's derive it first. So let's say I break it into these rectangles that have the width of delta. So they're equally spaced. So this is delta, delta. And let's say I choose the delta, so I have an integer number of deltas within the A to B. That's nothing fundamental, really. So I make these rectangles, right? Okay? So these rectangles, all of them have a width of delta, 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 whatever. And the area is approximately the sum of the areas of these rectangles, right? It's an approximation. So I can say my area, if I'm interested in the area, is approximately, roughly, the sum of these things. So what is the area of the first rectangle? This is the value of the function at A, right? So this is f of A. So it's f of A, lowercase f of A, times delta, plus f of A plus delta, which is the value here. So this is f of A plus delta, times delta. And so on and so forth. And the last one is, I guess, f of A plus n delta, or let's can say f of B minus delta times delta. Right? That's roughly the area. Now, okay, fine. But I know one more thing. I know f of x is related to this capital F of x, and the derivative of that. So what's an approximation of the derivative? What is the derivative? Derivative is the value of the function and its value a little bit farther away divided by the difference, right? By definition. So I can, while I'm doing approximate things, I can write f of a as the value of the capital F at this point minus the value of capital F at this point divided by delta. That would be the definition of the derivative. So I can write this definition here. I can say, so this is really f of a plus delta minus f of a divided by delta times delta, plus next one f of a plus 2 delta minus f of a plus delta divided by delta times delta, and so on and so forth. So at the end, I will end up with f of b minus f of b minus delta divided by delta times delta. So this sum is actually pretty interesting because what it does, it shows you that you can see that these terms start canceling out. So for this term, you have that term, and so on and so forth. So these two cancel and these two cancel. The only thing that's left, so now these two are equal, is f of b minus f of a divided by delta times delta. So now, to make this more accurate, what do you do? To make this more accurate, you can make delta smaller. As I make delta smaller, these rectangles become smaller, so these areas of error, which is the source of error, become smaller and smaller. So in the limit of delta going to 0, this area would be exact. So this would be exact if delta went to 0, right, for this whole thing. Which identically is the same thing. And in this case, since if delta goes to 0, it doesn't matter anyway, so it's going to be f of b minus f of a, which is, by definition, this. So this shows, this is the fundamental theorem of calculus. Now, this is very remarkable if you think about it, and very profound, because it says that you can determine something about the behavior of this function over a range of values by looking at another function related to it only at its boundaries, only at 2 points. So it says that these 2 points, capital F of A and capital F, has all the necessary information as far as the area is concerned for this. By looking at only at these 2 points, has all the information about how it behaves and how it moves around and all those things is captured by that. This is very interesting if you think about it, that it does that. And again, it makes sense. You can also I can also trivialize it for you. The trivialization is that this is a sum of all the area up to that point anyway, that f. So you're just saying, okay, if I integrate it from some negative infinity up to this point, I can know that what the area is up to this point. And if I know it up to this point and up to that point, if I calculate the difference, it's basically what is between these two. So you can make something very trivial or make it profound, depending on how you think about it, how you think about it. But if you don't make it trivial, and if you think about how this kind of things generalize, then you can actually arrive at more fundamental results and more general results. So this is a very special case of something else that you can write this way. So now I'm going to write it, the omega. So does this mean anything to anybody? Okay, so I wrote some things. I thought, okay, what? So she wrote a bunch of notation, okay, pretentious stuff. Yeah, do you want to say something?
Is it basically that the integral about like the line integral like about a closed path is equal to like the integral of like some quantity over like that same field over the enclosed?
Right. So you're saying that it relates to integral of over a line over integral over the surface, something like that. It means that it means that too. It means a lot more than that, but it means that too. It subsumes that too. So let me say what this says verbally in words, and then I'll show you examples of that and tell you. This says that in general, so M is a manifold. What's a manifold? It's kind of like an nth dimensional surface, volume or surface. It's a generalization of the same. So a line is like a one-dimensional one, and a surface is a two-dimensional one, and a cube is a three-dimensional one, or not cube, I mean any shape in 3 dimensions and all those things. So it's any surface or any shape. So it says the integral of the derivative over the volume of a manifold is equal to the integral of the function on the boundaries of that. So now, the first example is this. The integral of the derivative, which is this f of x, is the lowercase f is the derivative, right? In that case, omega is that capital F, right? The derivative function over the volume, a volume of a line is just the line itself, right? So it's a one-dimensional thing. Its volume is like one dimension, the line itself, is equal to the value, the integral of that, or average of that function over the boundaries, or the algebraic average. So it's FB minus FA, because one is coming in, one is going out. So that's a one-dimensional. What is it in 2 dimensions? It is the Stokes theorem. The Stokes theorem says what? The Stokes theorem says if you have a closed path, and if you integrate the function, so let's see. If you integrate the flux out of this closed path, right? So this is the flux, this is ds vector, and then the flux of a function f, right? The flux of a function f times ds over that surface is equal to the double integral, over that surface, the double integral is equal to the, I wrote it backwards. So the integral of f ds, okay, over the surface, so this is a surface integral, double integral, equal to the integral of the derivative of this function. Okay. I'm making this mess. Okay, so sorry. Never mind. Disregard that. So if you have the closed path, if you have a ds here, and this is the function f, it says that the integral of FDL, f times dl, f times dl over the line integral on a closed path equals to the double integral over the surface of curl of f times ds. Right? That's the Stokes theorem. So what it is that this is the derivative, right, on the surface, in the volume. Now, the volume of this two-dimensional thing is its surface, right? This area, this is its volume. Its boundary is this line. So you're integrating it over boundary, the function, and its generalized derivative. So it's really a generalized derivative. It's basically what we call a k form and k minus 1 form derivatives. So that's what it is. Now, if you take it to the next level, you can actually do it. You arrive at the, so this is the curl. Sorry, correct that. That should be curl. Now, the next level up is the divergence theorem. It says the integral over volume of the divergence of the function f, the vector function f, over the volume is equal to the double integral over the surface, the closed surface of that function ds. The flux coming out of something is equal to the divergence, and so on and so forth. And you can get it to the nth order, too. So this is important because it's a way of thinking about these functions and the derivative. And this is a useful way of thinking about these mathematical functions. Now, why did I talk about this? We'll see in a little while. Because we want to think about some of the singularity functions that we'll talk about. So what we will be using, though, is the singularity functions. So what do we mean by those? Let's start with the simplest of all the singularity functions. The first one we are going to talk about is what we call the unit step function. Unit step function. So what is a unit step function? The unit step function is a very simple function, really. You can define it as a function of time, because we will be, I mean, you can define it as x, but we use t because a lot of these things are used in time. u of t. So u of t is defined to be 0 if t is smaller than 0, and is defined to be 1, its value is defined to be 1 if t is greater than or equal 0. Now, what happens exactly at point 0? You can have it at different values. You can have it 0, 1. We try to keep it this way because this helps you with some of the subsequent notations that we'll have. It simplifies some of certain things. So it's this function. So u of t. It's called a unit step function because it's like unity height. It's a unit step. Right? Nothing really out of the ordinary. But let me ask you a question. So if this is u of t, what is u of t minus 1? 1 second, really, but u of t minus 1, let's say. How does it look like? So how does it look like? Yes?
Shift a step over
to the right or left? Shift a step to the right. Exactly, correct. Why? Why right? Because you have to think. Go ahead. Sure, that's one way to think about it. You're shifting the axis to it. Or basically, your reference point is point of when the argument of this thing becomes 0, right? That's when the switching happens. When does the argument become 0? At what value of t? 1. So that would look like this. So this is u of t minus 1. What is u of t minus 2? U of t plus 2. U of t plus 2 looks like this. So if this were 1, this is negative 2. So this is u of t plus 2, because at t equals negative 2 is the switching happening, right? What is the u of minus t? What does it look like? It flips, yeah, exactly, it's the mirror image. It flips horizontally. So this is u of negative t. What is the u of, so this is, if you guys get this one right, then we're good. So what is u of 1 minus t? To the left or to the right? Think about when the argument becomes 0. That's the switching point. To the left or right? Left or right? How many people say left? Raise your hand if you say it moves to the left. Raise your hand if you say it moves to the right. Okay. Think about it. At what value of t the argument becomes 0? 1 or negative 1, right? So that needs to move to the right. So this is like u of t minus 1 minus t. Okay. So that's the unit step function, and this is a very useful function, and you will probably spend a lot of time with this function. You will become very familiar and intimate with this over the next several weeks and years. So, okay, nothing very exciting or out of the ordinary. There's another function you can define, which is the pulse function. Let's call it p sub delta of t. Now, p sub delta of t is defined this way. So it's basically 0 for t smaller than 0. It's 1 for t greater than 0 or equal, and then smaller than delta. And it's back to 0 for t greater than 0, delta. Right? So what that means is that it looks like this. I think you need to visualize a lot of these things. This is nothing extraordinary, really. So this is 1, this width is delta, and the height is 1, this is t, this is p sub delta of t. So it's a pulse function. It's a pulse function. And by the way, can you write p of delta in terms of u of t, u's, in terms of unit step? Can somebody express p of delta in terms of u? P delta of t equals something that's written in terms of the u's. the unit steps. Anybody? Yes. So say again, u of t, u of t plus or minus u of t minus 1, right? Think about it. This is u of, again visually, this is u of t, right? This is u of t minus 1. This minus that gives you what? Here 0 minus 0, you get 0. Here you get 1. Then you get 1 minus 1, you get 0. So actually it shouldn't be u of t minus 1, should be u of t minus delta. So I made a mistake here. Right? Shifts by the delta, so it gives you delta. So this is delta. Yes?
Could it also be u of t times u of t minus t?
That would give you, the product would be 1 here, right? So that would become u of t minus delta. The product of these two, right? 0 times 0.
Times u of 1 minus t.
You could do that too. You could write it as, okay. So that's another one. So she says, and I think you said something along those lines first too. So you said u of t times u of 1 minus t, right? Which is this times that. Yes, you're absolutely right. You can write it in those two, as a product of those two. However, this is a lot more useful than this. Why? I claim that is. Go ahead. Superposition. So we found our designated superposition person. Just no, I won't. So anytime when the answer is superposition and nobody answers it, I would point to you. Okay, superposition, because now you can, this way you've written it as sum of two things. As long as you're dealing with a linear system, you're looking at the response. You have simplified this in terms of two things. So if you know the response to this guy, you probably know the response to this thing too. Then you can write the response to this as a sum of the two responses. Yes, go ahead.
For example, u of t squared minus 1.
U of t squared? You mean the time squared?
Times squared.
Not u of t. U, not the u is still squared.
U in parentheses t squared minus 1.
Oh, that's a good one. You know, he's throwing me curveballs. Okay, good. He's asking, can you use u of t squared minus 1? You mean like u of t squared minus 1? You can, but that's a shift in time. That's a warping of time. It is. You're compressing or stretching time, the time axis.
Because it's pause in terms of the step.
Correct. You could do a lot of interesting things, but that also kind of like messes up a lot of other things. So your responses will get messed up, but it doesn't mess up linearity, right? So superposition still holds, but your responses to these things, if your time base changes, then they are not going to be expressed as simple things like exponentials and things of that sort. They will be described in terms of other functions, and you can play with those. But it is going to be an interesting one. Yeah. Okay, good. Any other questions? All right. So let's continue. Now, this is the pulse function. So now I want you to pay attention to this thing. Now, what happens if I take this pulse? You remember, I can make things with these pulses, but if I take the pulse and scale it by delta itself. So let's say I look at 1 over delta of p of t. So in other words, it's the same function except for the fact that its height instead of being, so its width is delta, but its height instead of being 1, its height is 1 over delta. What is the area of this function? If its width is delta and its height is 1 over delta? What's 1, irrespective of what delta is, right? So now what if I take the limit of this thing and make delta very small? So let me just put it somewhere cleaner. It deserves its own space. So limit of delta going to 0 of 1 over delta p delta of t. I get something that becomes progressively taller and thinner, right? I can make it very, very tall, and in the limit, it becomes a point, right? So this thing is defined or called the Dirac delta. This is the Dirac delta. Now, Dirac delta is 0, so delta of t is 0 whenever t is not equal to 0. Right? At all times, because the delta has become very small, so it is compressed to 1 point essentially. And it is indefinite or undefined. Its value is undefined at t equals 0. But what we know about it is something interesting and useful. So what we know is that if you take the Dirac delta and look at its integral from negative infinity to positive infinity, what is that value? What is the area under this delta? 1, because of the way we defined it, right? Independent of the delta value of capital delta, its area was 1. So its area is 1, which is also equal to integrating from 0 minus to 0 plus. Because all the action happens around 0 for delta, right? It's 0 everywhere else. So it's, as long as you're a little bit before and a little bit after 0, that would give you an area of 1. This is another very, very important function. Now, let me ask you this question. What is the integral of delta of t from, well, let's put there, from negative infinity to t? Think about it. If I start from negative infinity and start integrating, right? Let's say I'm at negative infinity plus some value. What is this? Yes?
Unit step function.
Yes, you get a unit step function, right, exactly. Do you want to say the same thing? Yeah, okay. So, unit step function, but why? Think about it. As long as t, this t, is smaller than 0, there's nothing to integrate, it's 0, right? So it gives me 0. Once I cross 0, what do I get? 1. Once these limits include 0, so this is the delta, it's shown this way, by the way, this is a symbol. So as long as I integrate from negative infinity to here, I get nothing. As soon as I get past 0, I will include this in my integration limit, and then I get 1. So this is simply u of t, right? So the integral of this unit impulse is the step. And conversely, if this is true, then this must be true too. Delta of t is the derivative of the u of t. Right? So there's another way of defining delta of t. This is another way to define it, if you wanted to. So, by the way, we use this notation, and let me introduce it here, and it will be a little bit dormant for maybe a couple of lectures, and then all of a sudden it pops up and it will be everywhere. So we'll use this notation, right? So we have this operator, p, which is basically, operator p means differentiation with respect to time. So this is operator p operating on u of t. So when I say p of u of t, means this is an operator, operator is one level above a function, right? If you think about it, a function takes a value, a number, and produces another number for you. An operator takes a function and produces another function for you. So it's the one level up. So this operator takes this function, produces that function. Basically, this operator is differentiation. And the inverse operation is shown, which is the integration, which is shown as 1 over p. This is a symbol. Okay? At this point, this is just a symbol. 1 over p, the whole thing is a symbol. which means integration. So this means integration, and this means differentiation. All right. So this delta and u of t, these are called singularity functions. There are a lot more. We'll talk about them. There's one last property of this thing that I would like to talk about briefly, and then we'll talk about it more extensively in the next lecture. So it has another interesting property, which is what we call the sifting property. So if you look at this integral, let's say integral from negative infinity to positive infinity of f of t, or tau, or t prime, delta of t minus t prime, dt prime. What is that thing? Or actually t minus t prime, t prime minus t doesn't matter. What do you get? What is that value? Why? Let's think about this function. This is a very special function, right? This is a very unusual function. Its value is 0 at all times, except for 1, for when its argument is 0. So would the value of this function matter when this is 0? So at what point does the value of this function matter? When t prime is equal to t. So I might as well write this as integral from negative infinity to positive infinity of f of t delta of t prime minus t dt prime. But now this integral is over t prime. So t is a constant as far as this integral is concerned, right? So I can take this constant out. So I can get f of t integral from negative infinity to positive infinity of delta of t prime minus t dt prime. So what is this integral now? 1. It's the area under an impulse at some point along that line, at point t. Right? This is 1. So this is basically f of t. It means that this function, this impulse, goes and takes the value of that function at that point, at point t, and sifts it out, and takes it out and allows you to use it for whatever you are trying to do. Okay, so we'll use this to do more stuff and have a different interpretation of this next time. So we'll go over this quickly next time. But so that's where we are. Any questions before we go? Yes.
I'm just a little confused about delta, because we defined delta t to be limit when.
You mean they're talking about this one?
Yeah, just the delta t, the limit delta t. So we define 1 by delta p plus the pulse times. So I'm not certain how that goes to 0 for everything.
How does it go to 0 for all other values? Okay, as you make delta smaller, this pulse becomes narrower, right?
Yeah, but it's a minus now.
It's a minus?
No, as in it becomes a line, right?
Sure, it becomes narrower and narrower, right? It becomes very, very tall and very short. So its width is delta. But when delta goes to 0, this width is 0. So it will only happen around time t equals 0. At any other time, it would be it would be 0, right? See, you're making this narrower. So that's why that's why its value is 0 at all times other than 0. You can go off.